That was okay. Let me. Actually, I want just URL of that and just try to log in with my ID. That's it.
Yeah, just a minute. I'll try to log in mobile and give you.
Yes.
Sorry, sir, I was just disconnected.
Yes. I just want that URL. Could you provide me in the chat
Which URL, sir?
of your portal? Like, if you copy the URL of portal, so I will try to log in with my ID.
Okay.
Okay. Thanks. Let me try it. I'm able
Yeah,
to.
I pasted it. You can check that. Yeah.
Okay. It's not open. Okay.
Is it working for you?
No, actually, the subscription is not given to my ID. Let's paste it. Okay, we'll ask to the operational team. Okay, let's start now the session. So in week three, I think in week three we have uh, what are the content like? I want to see that.
Yeah, I'll shall I read for you?
Yeah, actually, if you present that your screen, that would be good for me.
I'll try it from mobile if I can do that.
Otherwise, okay, it's still now not.
Yeah.
Sir, I have many doubts in week 2.
Okay, in week two only.
Yes, sir.
Okay,
You're able to see the screen?
yes. Okay, okay. So in week three we have linear operators, scaling and rotation. Okay, and eigenvalues and eigenvectors. Okay, and diagonalization of a matrix, power matrix visualization. Okay, okay, okay. That's enough. Oh, thanks.
Yeah. Shall I stop it now?
Yeah, you can stop now. So, Satyam, in which uh, could you tell me where in which activity you have doubt?
Sir, basically, I'm confused between a range, null space, nullity, and rank.
Okay, okay. Let me present my screen. Then we discuss. Okay. Hope my screen is visible, right?
Yes, sir.
Okay, so nullity and rank, right? First of all, linear operator. So is that clear? What is a linear operator? What is a linear transformation?
Yes, sir.
Okay. So linear transformation are nothing but, it is just a function, but function is from, R2 to R2, the space, vector space from R2. The functions, real functions, a kind of x square plus 2x. These functions are generally, from R to R. So there is no kind of, vector space word is there, nothing. It's just a field. These two are generally called field, if you remember in the week one. But here is a different thing is there. This is a function, but from a vector space to another vector space. And this function have a kind of property that if I will take a vector, let's say x, and another vector y, then it will be, linearized of kind of this one. If c is a scalar and x is a vector, in that case it is going to be c times t of x. If any function have this property, we'll call it as a linear function, sorry, linear transformation. And the operators are, if this, suppose I'm just changing the word here, vector space from R2 to R, then you can, mean to say a linear transformation where, both have the vector spaces have the same, R2 R2, the same vector space, then that is called linear operator, operating on the space. That's the meaning of linear operator. And the next thing is, these two are the, I hope you know this all, just use it. The first thing is that range and null space. Null space, and then there is a narration or a rank and nullity. So we know, right, as if you remember, that if you have function fx, then we know that x square plus 1, this function is, from R to R. So what is the codomain? If you know what is the codomain, domain and range for the simple function, Satyam or anyone? Do you remember that? Codomain, domain? No?
Where the domain where is mapping the range is called codomain.
So actually, what about the outputs?
Yes,
Nothing.
yes.
The outputs, collection of output. What it is going to be. If you substitute 1, 2, 3, 4, or square or root 2, anything, you will get the outputs. One, if you substitute 1, you will get 2. If you substitute 2, you will get 5. If you substitute to root 2, you will get 3. Like this, the collection of output. That this is in the simple function. Very similar to, exactly, not very similar, even we'll say the exact thing. Suppose I'm just writing a vector space, linear transformation, let's say. So here is, this is a, this is a vector, this is a vector. It would be good if I read v1 plus v2, then it will be good. So here this is a linear transformation. Suppose you have a linear transformation where the, mapping is given like this, t of x, where this represent a vector t of v, where v is, v is your xy. So this is one. So the expression between the coordinate is given like this. This linear transformation is from, it is a linear operator, from R2 to R2. So let's say x plus y and x minus y. Suppose this is a linear transformation we have. Okay. Now I'm just giving the output, input. I'm just giving the input. Let's say I'm just giving a vector t12. This is from a vector. So generally we double, in place of double vector, I'm just keeping one single, bracket. So just t of 1 2, this is, this is x coordinate, this is y coordinate. So this is going to be 3 and this is going to be -1. Similarly, all other. So what are the possible elements in this here input set vector space v2? Okay, and corresponding this output. So this is suppose your v, then we are getting this output. Similarly for all. So just collect all. Okay, I'm just collecting all outputs tv. I'm just collecting all output, whatever input we have given from the vector display. I'm just collecting those all outputs. So this is called range of the linear transformation T. For example, let's say I'm just, so let's collect what is going to be the range of this one. What is going to be the range here?
Minus
So
3
if
to
I want
minus
to put it in the set form, so then in that case, can you tell me what is going to be the range? It is going to be whole R2, this one, whole R2, or it is going to be subset of R2.
Okay, so it will be the R2, complete R2, correct?
It will be complete R2. So
Yeah.
is that clear what I am talking here? Range is clear. We'll check it. It is going to be whole R2, or I don't know what is going to be. But is this clear? Range?
Yes, sir. Yes,
Okay.
clear.
So now, how will sure that the whole R2 it is going to be? So how you are sure this is going to be whole range is going to be, means to say any, I mean, for all elements. So all element could be, you know, of all element could be generated, like all element of this could be get from, you know, whatever they give input will get all element. So how will sure this? So to sure this, do you remember that in the last, I think in week 2, even the week 2 itself, matrix representation of a linear transformation? I think it is in week 3 or week 2. I think it is in week 2.
2, sir.
Week
Yes.
Matrix representation. So what is going to be week 2? Or sorry, matrix representation of, if you remember this, what is going to be? How we'll get this? First, the basis of R2. Basis is going to be 1 0, canonical basis, okay, and 0 1. We'll
Yeah.
take the canonical basis and we'll find the image of that canonical basis element, whatever we have. So image of this is going to be 1 0 is going to be 1 and image of 0 1 is going to be 1 and minus 1. So matrix representation is generally what is called, we'll just express in the respect of canonical basis, and this is here 0. We can write like this, right?
Yeah.
It is correct, right?
Correct.
And this is, we can write 1 0 and this is minus 1 here, minus 1 0 1. Correct? So matrix representation with respect to the canonical basis is going to be, you know, whatever this one is going to be here and whatever this one it is going to be here. Okay? And whatever this is for the second, okay, this is for the first one, this is for the first canonical basis, this one 1 0. And now we'll check for the second one. For this one we got this here, so this one will be here and this one will be here. This is the matrix representation of this T, matrix representation of T with respect to canonical. Okay. Now, if then in that case, what is going to be now? Will all of you do the row operation, right? The row operation, if you remember that, it will explain you the rank also. We'll try to explain rank and range. So
if
this
rank
is going to be what? I'm
if
just
the
doing. Sorry.
if the rank is 2, the range will be R2. That's what mapping it is.
Yeah, that's I want to tell you.
Yeah.
So I will try to convert this. I'm just doing the row operation and try to make it here 0. If you remember in week 1, I had solving the system of linear equation. So R2 minus R1. I'm just doing this. So we'll get here 1 0, and this is 1, and this is minus 2. So we are in that track. This is of triangular, upper triangular form. So
But
this tells that.
no, just a minute. This will be the column operation because our coordinates are in column. It is arranged in the column wise, correct?
Yes.
Yeah. So so you have to invert the column to row, then you can do this operation directly.
No,
Or
nothing. I'm just not. There is no column or row operation. I'm just doing this row operation. We'll try to do only the row operation mostly.
no, I'm just confused here that as per professor lecture, he was saying that one in the column, it will be a coordinate of one point there, correct? So you have to you have to operate on that column wise, or is it by row wise?
You are saying we wrote this in the column wise, then we have to do in the column wise.
Yeah, that's what I think, because that's what professor was saying in another lecture, that if we are finding it difficult, we can rearrange the coordinate in the row wise and then do the operation and check for the
Yes.
range. Yeah,
So
something
we
like that
can do
you mentioned.
actually. So there is no issue. We can do. There is no issue. So either we can do or column. That's fine. That's totally fine.
Okay.
There is no issue. Okay. So we can do.
Yeah.
Okay. So here I am doing just row operations.
Okay.
So here this tells you the rank of the matrix is 2, correct?
Correct.
Two independent row. We got with this fashion number of this tells you that if suppose this is 0 here, by chance this is 0 here, then in that case row is going to be 1, correct? Sorry, row culture. Sorry, rank is going to.
Yeah, 1 non-zero row is there, so it will become one. Yeah.
But our case is here we got -2. This tells you rank is 2. And if the rank of this linear transformation is 2, then in that case, range of this linear transformation is going to be whole R2. That's the thing here. So this tells you that now you can say that the range is going to be whole R2. Suppose the case I made here plus also here. Okay, so this is for -1. Okay, so let's try another example. T of xy is equal to, I'm just making x plus y and x plus y both. What is going to be the range here? I will get this range. Any idea? The same process will follow.
Yeah.
So if you same process will follow here, then T of 1 0 is going to be 1 1, and T of 0 1 is going to be 1 1. And corresponding matrix representation is 1 1 1 1. Correct?
Yeah. So this is rank 1 and null is 1. Yeah.
So this tells you if you do that, we'll get the row operation R2 minus. If you do the row R2 minus R1, we'll get here 1 1 0 0. And this tells you rank is 1. Correct?
Yeah.
What is then the range? So yeah, it tells you the rank is 1. So what is the range now? Can we get that set? That range. Range is a set, right? Range is not only set, it is a subspace. It is a subspace of R2. What is going to be the subspace that?
This could be one line on the.
This could be one line. That's correct. It is a line. It is a line, and it passed through origin. Subspaces, and I think in the first session I took and said that subspaces of R2 is only the line which passed through origin. So this line is passed through origin. What is that line?
So that line could be x plus y Yeah, x equal to minus y. That could be. I think y is.
No. So
No.
what is that? You just we got this matrix. Just multiply with matrix. Sorry,
Oh,
x y,
okay. Yeah.
and you will get here what a x plus y.
Y and 0.
So that line, what you have, x plus y and 0. X y belongs to R.
Okay. Okay. In this case, the nullity, how it makes sense?
I'm just missing them. Sorry. I just missing that. Just a second. Okay. No, not here. Sorry, not here, not here. Okay, not here. So I just take that matrix and multiply with this one. You'll get x plus y, x plus y. So same whatever you have. This is the actually this is the same range here. Whatever you have, no, you just need to write in the set form. Just need to write in the set form. X plus y, x plus y, x y belongs to R. Either this or from here itself, it's this is the range. So that line, if you want to represent in the line form, how we'll get, because these are the same, right? So either you can write like this, just like x and x. Either we can write like this. This tells you a line, right? This is the same thing. Represents the same set. Confusion? Still confusion, or I don't? Is this clear? Is this clear?
Yes, sir.
So this is the range. Either from directly you can write this one in the set form, that's fine, or we can do from here. Is the same meaning is there. See, matrix and you are multiplying a vector, this tells you the image, the same image it gives. Actually, you want to find the image of 1 2. This means that your image is 2 3. Either you do from this, or you have the matrix, okay, of that linear transformation and find the matrix multiplication. So
So
this is going to be
this will be basically y equal to x line as per this coordinate.
this is this as per the coordinates. This is x is equal to y line.
Okay. And in this example, the nullity is 1. So what that signify? I mean, yeah.
So yes, from here, rank we clear. Okay, range and rank is fine. Now nullity or null space. So what is the nullity? Nullity is the dimension of null space. So we have to find first the null space. And the null space, what we'll do, whatever we did the row operation, this one, correct? We got this matrix. Now what I am doing here, we got this one. Okay, we got this. So to range, we did this one. To range, we are doing actually this for range. For nullity, we'll do after this, and then we'll take multiply here, and this we got, correct? This will get here. So this means that this tells okay. So actually, what is the meaning that we'll got? Actually, what we will do? Nullity is that. Sorry. Actually, null space is the. Let me write the definition first. Null space is the those vector collection of those vectors from the domain space. Okay, such that image is 0. This is the only null space. Null space is the those that TB R2 to R2 from this one collection of those vectors from this domain. Okay, where that image is 0. I want to collect only those vectors, and this is actually a subspace. Okay, this is a subspace of R2, your domain. domain space, subspace of your domain space. Okay, is this clear?
So as per then, other than the line, other than the points which is falling on the line,
Hmm.
each point will be mapped to the zero. I mean the origin to the after the transformation.
After the transformation, you will get the images as 0.
Okay.
We'll check here. Okay, we'll explain or we'll see it here.
Yeah,
So,
that's
so this is the null space, and as you know, we are saying this null space is subspace. So dimension of this null space is called nullity. Dimension of this is called nullity. We'll do this. We'll give the formula also. Rank nullity theorem. Okay. So we have this linear transformation P of x y is equal to x plus y and same x plus y. Okay. And we so to find the null space, we first find the matrix representation, which we have this one. Okay. And now what we are doing, I just said, right, to get the image, we'll do multiply with the, to get the image, this is just doing the matrix multiplication, right? This and this, general vector. This is the general vector. And I'm saying the image is equal to 0. That image I'm saying, this is the image of any general vector, and this is equal to 0. Correct?
yeah.
That's I'm doing here. I'm taking a general vector and I'm just equating to 0. I will explain from directly here also, but let's do first on matrix. Okay, on here, and then back to, I will connect to here also, and you will see that it is actually the same. Whatever we are doing here, we are organized way, organized way, but here we are doing will here we'll do with the multiplication. So is this clear? This is the meaning.
Yeah.
Yes, sir.
Now let's do the matrix multiplication. We'll get here x plus y and x plus y. This is equal to 0, 0. That image going to be origin. And this gives you x plus y is equal to 0 and x plus y is equal to 0. Both separately will give just comparison. And this give you the same function is there. That means you have this. And this means that x is equal to minus 1. So that means null space is that line. Null space is this line equal to minus y. Okay. And if I will try to write the function on the set form, null space is the set x comma minus x, or there are many ways, x comma y, such that x is equal to minus y. Many ways to write the set. Either this one or x minus x, that x belongs to R. These are actually the same. These two are same. So this is your null space. And if you see what is the dimension of this, what is the basis of this null space? Could you give me the basis of this null space?
One, sir.
No. It will be in the pairwise. No, it how it could be a real number? It could be a pairwise.
Since it is saying x equal to minus y, so I mean it will be the 1 and minus 1 and
Yes. So it's better to like this 1 and minus 1. We can write this right as like this
yeah.
one, and then x belongs to R. So this is your basis. No, this is generating. This is the important. This is any real number. This is your generator. And so basis is 1 minus 1. Basis of your null space is this one. and number of element in the basis is 1 only. So nullity is 1. Dimension is the number of element in the basis. Clear?
Yeah.
Is this clear? Nullity? How it is nullity is 1.
Yes, sir.
Now see, this is the way to find using the matrix. No, this is I did for all for matrix. Now let's do from here linear transformation. This is our linear transformation.
Sir, how here 1 comma minus 1 came, sir, for basis?
This is the no. This is the set I took. This is the null space. I just take it out here,
Yes.
and this is the same
Okay.
thing. Right? I'm just multiplying x with the vector 1 minus 1.
Yes, sir.
And see, this is any real number. I'm just multiplying the vector with 1 minus 1. Our this gives the null space. That means this is our generator, right? This is our main thing. Because of that, we are able to just multiplying real number and getting any vector of null space. Correct?
Yes, sir.
So that's why this generator is going to be our basis, element of basis. Exactly, one generator is there. That's why the nullity is 1. Still doubt is remain, I think.
No, sir, it's clear.
Clear? Now let's do on this linear transformation here. From here, we did on matrix. So we know that the null space, vectors such that their image is 0. So our vector is, let's assume the general as we have this we assume. So our vector, let's say p of xy is the expression itself, x plus y. And this tells you that image is going to be 0. That means that let's assume that for general one, this image is this, and this is equal to 0. And this tells you x plus y is equal to 0, x plus y is equal to 0. Just do the comparison coordinate wise. And here we reaches to here, this one. So before going to from matrix style, we directly jump to if expression is given, just expression equal to coordinate 0 0 0 and write this separately. This will give you the null space. So it's both ways clear, either from matrix or directly from the linear transformation.
Yes, sir.
Now let me tell you the connection also, the rank and nullity relation. I think sir is named out else. Rank theorem. And what is the rank nullity theorem is that previously we remember the rank 1 for this one earlier from here. We got that rank is 1. So directly we can use that. What is the rank nullity theorem? The theorem is that rank of a linear transformation, nullity of a linear transformation, okay, equal to number of what? For the matrix, number of columns in the matrix. Columns in the matrix. So we got the rank of the matrix is 1. Nullity we want. Let's assume as a variable nullity. Number of column in matrix is number of column means this is our matrix is only 2. So 2 cross 2. So here is 2 only. Rank plus nullity is 2. Our theorem is this one. Our main theorem is this one because we are playing on 2 cross 2. So rank plus nullity is 2, and that's why the nullity is this way. Rank nullity theorem minus 1, which is 1. The same we earlier did here. So by rank, after just going to the rank, we can use this theorem and directly jump to the getting the nullity. this theorem only give the rank and nullity. Okay, it will not give the null space. It will just give the information about the nullity. Okay, is this clear?
Yes, sir.
So this is the use of rank and nullity theorem, and this is all about the rank, range, null, and nullity. There are 4 words, so keep in mind that these all 4 words: range. The dimension of range is rank, null space, and dimension of the null space is null. Okay, now see that how the element is going to be the origin. So for example, we can take a vector, let's say 1 minus 1, and if you find the image of this, see that how it is going to be 0. Our image is x plus y, that whatever the output. So let's do here 1 minus 1 or 1 plus minus 1, 1 plus minus 1. That's the here expression is happening of x, y. And that's why it is going to be 0. See that a non-zero vector went to a 0 vector. And that's why this is an element of null space, or vector of null space, which is already said even basis itself. Even any basis, any vector of this null space is going to be a basis. You can take this vector also, 3 minus 3. See the image, 3 minus 3, 3 minus 3, which is 0, 0. Non-zero went to 0 vector. So 3 minus 3 is an element of the null space. Even this is also a basis, because one dimension subspace element is going to be a basis. This is also basis. Is it clear? I'm saying the word.
Yes, sir.
Please stop me if it is not. Okay, if anything is missing or anything you are not getting, I'm surely explain you. Please let me know. Once please let me know that if you are not getting anything. I mean, a small thing.
See, one doubt: the basis, at least minimum 2 vector is required, no, for the basis to be defined.
No, for one dimension only one.
Okay. For one
If it
dimension,
is
only
one
one.
dimension, as here said, it is going to be one. Only one vector.
Okay, understand. Yeah.
Okay,
And
so
sir,
this is all about
explain.
range.
Yes, sir. Sir, you explained about matrix representation.
Here, this one. Yes.
So could you explain a little bit more about matrix representation of linear transformation?
Okay. So let's discuss with another example. I'm just taking a linear transformation. X plus y is equal to x square. I mean, x plus 4y, and let's say just y and just y. Suppose this is a linear transformation you have. I want to find the matrix representation of this with respect to the canonical basis. The full question will be like this: find the matrix representation of this linear transformation with respect to canonical basis. Our canonical basis of R2 is fixed 1 0 and 0 1. This is our canonical basis. This is your V1, this is your V2. Canonical basis of R2 is this one only. So let's find the image of the canonical basis element T of 1 0, which is 1 plus 0 times 4, and this is 0, which is 1 and 0, even itself that. And let's find the image of the second one. So this is 0 plus 4 times 1, comma 1, which is 4 comma 1. Okay, so the way is that whatever you find the image, express that image with respect to the basis. So expressing is that, let's say the expressing is the exactly the same, 0 time 0 1. If you see, this is the same, correct? Without expression you cannot write here the entries. Okay, entries will come the coefficients of the basis. Okay, not clear, I think. Not clear?
Clear, sir.
Here if I want to write this 4 1, so if we try to explain this on the canonical basis here, so this is going to be 4 times 1 0. And why I am saying this expression is, I will tell you that why it is I am saying you. Okay, so this is the expression expressing this with respect to this canonical basis. Now entries will be this one will go to the first here, and this one will go to here, this one will go to here, and this one will go to here. This is the matrix representation. If you see, this is just writing this vector in the vertical form itself. It is, just writing this vector, you will get here 1 0, right? This is the vector image you got, 1 0, writing directly to the same place here. And this is the image of this one is, even is, it is writing in this fashion. We should to write in the vector in this fashion, but we can write this way also or this way also. So here is 1 plus 0 times 4. Oh, sorry, here is what is that, 0 plus 4 times 1 and 1. So that means here 4 comma 1, which is directly writing here. There is no, then you will say why we are expressing this by this, and then you are saying the reason is, if I will change the basis to different from I will just write another basis of R2, not canonical basis. For example, let's say 1 1 and 1 minus 1. This is another basis of R2, but not canonical. This is not canonical basis. Okay, canonical basis our is this one only, 1 0 and 0 1. With respect to that, this matrix is this one. But my question is, what is going to be the matrix representation of T with respect to this basis? Could you tell me? It is going to be different. We'll do that. We'll do here, but it is going to be different. We'll see it. Are you able to catch it? The differences, both of you?
Yes, sir.
Yeah.
So let's do now. Let's find the matrix representation of T with respect to this basis. This is not a canonical basis. So the same process will follow. We'll try to find the image of that basis element. And our expression is the same here. This one. P of xy is equal to x plus 4y. Let's find the image of this one with respect to this expression whatever we have. That's the process. It's going to be 1 plus 4 comma 1. This, which is of this one, which is 5 comma 1. And now we'll try to express this vector. So we have to do this. Okay, how we'll do this? It was easier here, but it is not now easy here. It is going to be here A, your 1 1 with respect to corresponding to 1 1, and this is B 1 minus 1, because we want this coefficient, right? Then it is going to be. And let's find the second one, which is 1 minus 1, and this is going to be 1 plus 4 into minus 1 and minus 1, which is minus 3 and minus 1. What is going to be here your A prime with respect to 1 1 plus B prime 1 minus 1? Then your matrix is going to be A here this and B here this and this coefficient. A prime this one prime this one. We have to find this A prime, B prime, A and B. What is going to be those? Can you guess what is going to be those?
Yeah, I think we need to find the equation for both the
Yes.
and then
Yeah, and then solve and then find A and B. That's all. That's the only way. That's the only way. Just a second. So is this clear? We have to, the process is that, we have what, so the process is we have to find the equation. So what is that? This is going to be 5 1 is equal to A plus B and A minus B. Correct? This tells you A plus B equal to 5, A minus B equal to 1. And now we have to solve this. Solving is, I hope it is easier, just adding these two. So this is 2A is equal to 6, A equal to 3 we get. And now we'll substitute any one of them, we'll get the B value also. So here is going to be 3 and B value. Whatever we'll get here, B is, I think, A plus 3 is equal to 5. Sorry, 3 plus B equal to 5, B equal to, we'll get here 2. So here is 2. Similarly for A prime and B prime will do. And this is going to be your matrix representation with respect to this basis. So this is the difference between the canonical and the normal basis. Okay. So canonical is much easier. Whenever in the question canonical is asked, you can directly write in the vertical form. This one, you can directly write it here and here. But when it is different from the canonical, then your work, then you have to do more work here to solve equation, then get values and then substitute. This is clear?
Yeah, this is clear.
Yes, sir.
Okay.
Yes, clear, sir.
And that's the only way. Okay. Any other doubt?
Yes, sir. In change of basis,
Hmm.
yeah, if you explain it, then.
Change of basis. So what is the change of basis is, yeah, so here is what is, here is one thing is happening. One basis is, let's say I am just saying b1, which is 1 0 and canonical basis. This is a basis. And another basis is 1 1 and 1 minus 1. This is another basis. Okay. So what kind of question is there? Change of basis in what? What is your exact doubt?
Sir, explain change of basis. I'm confused in change of basis, how to proceed with, and I'm
Okay.
lacking concepts of change of basis.
Okay, so let me, I'm taking a vector of r2, let's say 5 3. Okay, I'm just, this is a vector in r2. Okay, so this vector with respect to this canonical basis is actually, this 5 3 is nothing but exactly 5 1 0 and 3 0 1. So then the best way is coordinate. This is called coordinate. Okay, coordinate of this vector, let's say this 5, I'm saying 5, this v, so the coordinate of this v vector with respect to canonical basis is exactly the same, 5 3. Okay, this 5 3 coordinate is generally, writing like this. Even the horizontally also we can write, but anyway, okay, don't worry, if it is in this fashion written, generally think that it is in the vertical or in horizontal form, it doesn't matter. But yeah, it will be separated by comma if it is in the horizontal way it is doing. So coordinate of v with respect to this canonical basis is this, but the same vector with respect to this is going to be different. I have this vector 5 3, which is v, our v is 5 3. What is going to be the coordinate with respect to this basis? This coordinate is, this 5 is, this 5 is here. Okay, this 3 is here. So what is going to coordinate for this with respect to this basis? Simply the same what just now we did. A time 1 1 plus b time 1 minus 1. And let's find that. And the coordinate is now of this v is going to be your a and b. That's all. This is the change of basis. Nothing more. The same vector with respect to canonical basis is the exactly same, but with respect to different basis is going to be different. Now let's solve this. This is going to be what? A plus b and a minus b, and this tells you what? A plus b is equal to 5 and a minus b is equal to 3. Let's solve this. Adding these two, give 2a is equal to 8, a is equal to 4, and now b value is going to be 4 plus b equal to 5. This give you b equal to 1. So what it means, that coordinate of this v with respect to this basis is what? 4 comma 1. This is the change of basis. This is the meaning. If base, your generator, is different, then your vector appearance wise, appearance wise is going to be different. What is the meaning of this? Previously, in geometrically, it will be easier to understand in geometric form. This is this coordinate, sorry, this one 0 1 and 0 1 is actually your this coordinate system, rectangular coordinate system, but it is exactly the same, as in coordinate system, if you whatever in the maths one you studied. But with respect to this one, your coordinate is now going to slightly change. It will be, I think, what, it is not this one, it is going to be of this one, slightly changed. Coordinate is going to be, yeah, but it is of this form. Your vector is somewhere here 4 comma 1, somewhere here. This is the different, this is the difference. Here it is, it is as your in the coordinate system, but here is slightly changed. That's the meaning here. Not clear, I think. Still not clear.
No, I am clear actually. I can understand, and there is no problem. Yeah. Satyam, you have to comment. Yeah.
Yeah,
Yes,
Sutyam,
sir.
could you
I also
please
understand.
understand?
Yes.
That's the meaning here. That's the meaning. Only this is the meaning.
Yeah.
The same vector with the different basis, it's look like different. Appearance. This is called appearance. That's why the change of basis there. Appearance is different. The same vector. In canonical, it's look easier, but when the basis is changed, basis is your generator. Your basis element is actually generating all element. When your generator is changed, the appearance is going to be changed for the same vector.
I was just thinking about the application. Then I was thinking about electromagnetic analysis and the field analysis. Is it used in that
Yes,
cases?
yes, it is going to be when the field is actually the same word field. I think so. It will work here. The field is whatever in vector space field and the vectors is their
Yeah.
word. So same is going to be field is change, space is change. Your
Correct.
appearance of the vector is going to be changed.
Yeah. Right. Yeah, there is concept in motor that is moving electromagnetic field. So
Mm-hmm.
we come across this kind of requirement, and so yeah, I understand it.
Clear? Now I think it is better now.
Yeah.
Sir, take an matrix and then do its basis change, means change of
I,
basis with
okay.
matrix representation.
Okay. So this is what I did, no? This is what I did. Change of basis. Matrix, and this is what I did, no? I took another basis. So this is the same. See, this is the linear transformation, and here is the same linear transformation. But with respect to canonical, we got this matrix. Where is that? Uh, this one, four. I think this one, yes. This one. With respect to canonical, this is the same. Sorry, this one. And this is the change of basis is happening. And when I am changing the basis now, for the same linear transformation, I am getting, see now the different 3, 2, and the a, we have to find a prime and b prime. See that the differences here. Let me make it with this one. Now see the entries of the matrix. It is changed now. This is the actually change of basis happening. I told here for the respect to with respect to the vector, and now this is respect to the linear transformation. Okay,
Yes, sir.
clear?
Yes, sir.
Okay.
Yeah, I think we can move to week 3. Some of the concept.
Yes.
Yeah.
If this is done, no, this is done, then week 3 is not a difficult thing. Okay. In week 3 we have let me open it that. In week 3 we have a linear transformation. Okay. Null space and okay. So composition will be discussed about the composition, and then a linear operator we have. I just in starting said the same space. Linear transformation is going to be on the same space. Then we call it a optical. The same word is there. Linear transformation and linear operator are the same word. Okay. For the time being, here we can go with the There is no change. And scaling and rotation, okay, this is just we'll discuss that. Main thing is that eigenvalues and eigenvectors.
Yeah. This one, yeah, I also wanted to, yeah.
And
Is this?
scaling and rotation, I don't think is needed. This is just a kind of the same linear transformation. Just a vector can be scaled or a vector can be rotated. That's the meaning here. So we can skip, even you can just watch and it will be more clear there itself. The thing is, I want to discuss this composition and then eigenvalue and eigenvector, these two.
Yeah.
So composition is, composition. Let's if you remember, even maths one itself, sir, is talked bit about composition of function. As there is a composition of function is there, the same composition of linear transformation is also there. So let me take an example. Let's say a linear transformation is given as x plus y and 2x minus y, and another linear transformation g, which is of let's say 2x plus y and x, uh, only just x. Okay. So composition of these two, this one, t of g of xy, this is going to be your exactly here, t of g and then xy. So what it mean that? It means that t of g of xy. So what it means that first apply g and then apply t. So what is the expression here? The expression is going to be what? T of so t of your g of xy is what? This one,
2x plus y.
2x plus y and then x. And now apply on here. So this is your x now. If I'm changing x prime kind of thing, and this is your y prime. So what is the relation in x prime and y prime? Here is, if I will write x prime plus y prime to x prime minus y prime. So that means here 2x plus y, x prime, and then y prime is added. So y prime is our x itself. Here, just see that here. And now the next is 2x is our 2x plus y, and y is our same x is there. So where is, that's the meaning here. This is your x and this is your y, and this is just match here. I'm just changed with the, if it is for the try to see it, the same thing is remain. Just in place of xy, I'm just writing this one and this one, and this is you're going to be 3x plus y, and this is 4x plus y 2y minus x. So finally expression is going to be 3x plus y and 3x plus 2y. This is the composition.
And the inverse of this will be the same. I mean, the same process we can do in the
Yes,
inverse.
same process. In place of writing that, just write that g inverse, sorry, t inverse.
Okay.
So one is, so this is the composition, but one interesting thing is there. What is the interesting is that, suppose matrix representation with respect to canonical, okay, with respect to canonical is, let's say this one, A, matrix A, and matrix representation of G with respect to B, sorry, with respect to canonical basis is your B. And what is the best thing is that the matrix representation of this composition is nothing but with respect to canonical, okay, with respect to canonical, if you try to find, nothing but A cross B. This is the beauty. Just multiply the separately them, and whatever the multiplication matrix you got, it is going to be the composed matrix of of that matrix representation of this composed linear transformation. This is the beauty of the linear transformation. Just multiply them separately of, as you we calculated here, or we just find the matrix representation separately. If you multiply them, it is going to be just position of representation of the composed linear transformation.
Sir, for canonical base only, na?
It is for the canonical. The base is going to be the same. If any one of the base is going to be, you are going to change. So this thing is only apply when you are doing on the same all three are on the same basis. Don't change any one of them. If you change, then you are confused. Even it is not true also. Okay, it is not going to be true. It is going to be the same for same basis for all three. All three. If you are saying, if you are saying for, except for the canonical, different basis b prime, so all these on the same basis. A is also find on the b prime, b is also find with respect to b prime, sorry, b is also find with respect to this basis, not canonical. And then c you will get, which is a cross b composition, is also will get with respect to this not canonical form. Okay, or you have to keep each time same if you are not taking the canonical. Okay, you have to maintain this.
And if it in a different basis, then you do something else also.
No, if you are saying your matrix A is with respect to canonical and B is for different, okay, then A cross B is not going to be your composed. Okay, it is not going to be your C. Okay, in that.
In case I have not canonical, but I have a different basis for A and B, but same. So in that case, we can do the same process.
Sorry.
No, what I'm saying, instead of canonical for A and B, I'm saying they're different basis, not the same, not a
Mm-hmm.
canonical node, but it is the same basis. So we can apply the same process.
Same process. That's why and that is what I'm saying. No, B prime
Yeah.
means not canonical, different from canonical.
Okay, understand. Yeah.
Okay, this is
Yeah.
one thing, and this is the, that's all the composition. Nothing more. Composition is just matrix multiplication, and you can check how the matrix multiplication. We don't. I'm not going to discuss this. This is a simple one.
Yeah.
Eigenvalue. Let's discuss eigenvalue and eigenvector. This is one important thing. So what the eigenvalue and eigenvector? So before to reach eigenvalue, first discuss eigenvector. Actually, eigenvalue is came after the eigenvector. Okay, eigenvector is more. Actually, it is informed from that once you know the eigenvector, then eigenvalue is very much clear. So what is eigenvector? So suppose you have a matrix. I am just doing from the matrix only. We can deduce we can infer the linear transformation. But let's do on the matrix first. So suppose you have a matrix, this one. Okay. Let's say I'm just writing 1, 2, 3, 4. Okay. This is the matrix we have. And suppose by sudden, I'm saying by sudden, okay, by luckily, by chance, I got a vector, okay, v, something is there. And what I get, I when I did the matrix multiplication, what I got, I just got same v here, same v, same entry, but some alpha time, some scalar is multiplied there, something is there, I just got this one, some number, I just do multiplication, I get the whole this matrix multiplication. If I will just do this one, in that case I just call v as, now I just calling this b is a eigenvector of this matrix. That is the definition of eigenvector, that's all. By luckily, yeah, by luck I got this v, but this is not luck. Okay, we'll try to get this how we are getting. And what is the role of this alpha is called your eigen value. Okay, this alpha is called your eigen value. So this alpha is actually came after the eigenvector. This eigenvalue is came after the eigen. Once we have to know first eigenvector, and then we'll deduce this eigenvalue. So this alpha is our eigenvalue, and now this eigenvalue will help to find the eigenvector. We'll slowly see the process. Is this clear?
Yes, sir.
So let's find the eigenvalues and eigenvector here for this one. So we have 1, 2, and 3, 4. This is our matrix. Okay. So what I am doing, so actually what we will do, no? So the process is that what is happening here will deduce from here itself. This is the thing. These things are happening here. So what I am doing here, I am just sending this to this side. We'll solving this matrix form equation. So what is happening here? 1, 3, 2, 4. I'm just taking this v as okay. So let's keep the same. This is minus alpha time the same. This v, and this side is 0, 0. Now what I am doing here, I'm just taking this vector common. So I will take vector v common. So I will get this matrix 1, 2, 3, 4 minus. I just this v I just took common here. Okay. So what will remain now? V. Now I am doing the matrix operation here. So what is happening here? No? Here you will get the identity matrix. Okay? If you take the common v. Why the reason is? Can you tell me why I am writing like this? Why this is will get here identity matrix? If you answer me.
Yeah, because it won't affect alpha if you multiply with that.
Yeah, it is just because we are doing on matrix operation, so it should be in the same order. If it is 2 cross 2, I have to maintain this. So if I am taking v vector as a common, so anyhow this operation done on vector, but I took v common, so it should be maintained, right? So that's why this identity matrix came to maintaining this operation on matrix. So this now this v is there, okay, and this will go what? This is same 1, 2, 3, 4, and this minus alpha 0, 0 alpha, and this side is 0, 0. And what is the next step? We'll multiply coordinate entries wise. Sorry, subtraction will be happen here entries wise. So 1 minus alpha, 2, 3, 4 minus alpha. Okay, and this v outside, and this is equal to 0, 0. Okay, so see that this v is multiplied here, and then you are getting this vector. So now what is the process? No, so to get the alpha, we'll directly find the determinant of this matrix. Just find the determinant of this matrix. So let's find this determinant of this matrix. So this is 1 minus alpha, 4 minus alpha, and this is minus 6 is equal to 0. We'll get here. That's the determinant. Okay, so we'll find the determinant of this and equate it to 0 to find this alpha value. So this is a algorithm, you can think it. Otherwise, if I will go in more detail, then more mathematics is needed. So from here, so only why I'm telling, I just telling you that this is, if you have a matrix A, then alpha time I, and find the determinant of this equate to 0. That's the process to find the eigenvalue if you see the lecture. Okay, so that is what I am doing. So find the determinant and equate to 0. So this is what. Now let's do this. This is alpha minus 1, or let's do multiplication. This is 4 minus alpha, and this is minus 4 alpha, and plus alpha square minus 6 is equal to 0, and this tells you alpha square plus minus 5 alpha plus 4 plus 4 and minus 6 is there, and this will be of I think minus 2, right? Is this correct?
Yeah.
And now I have to find the root of this alpha is equal to plus minus minus b, which is our minus 5 minus b, sorry, what is that? Sorry, no, sorry, minus b,
Yeah, it is 5.
root of b square, which is 25 minus 4 into a into c. That's the square root method upon 2 into a, which is 1. So here alpha is equal to minus 5 plus minus 25 plus 8 will get here, and this is 2, which is minus 5 plus minus root of 33 by 2. So 1, so there are two values, right? Here is two values we have. So one plus and another is minus. So alpha 1 is going to be minus 5 plus root of 33 by 2. This is one eigenvalue, and another eigenvalue is minus 5 minus root of 33. Right? This is another eigenvalue. Okay. So it is a bit tougher now. I just took a difficult matrix and I got a complex complex eigenvalue. I mean complicated eigenvalue. Right. So to take the easier one. I think I should to take the easier one. uh, I'm just taking another to reduce our calculation. Let's say I'm taking 1 1 and 1 2, and let's find quickly the eigenvalues of this. So to find the eigenvalue, what is the process? A minus alpha I, find the determinant. So we have 1 1 1 2, and then alpha time. So here is directly I'm just writing inside here 1 minus alpha and 2 minus alpha, and find the determinant of this matrix and equate it to 0. So this is 1 minus alpha, 2 minus alpha, determinant, and this is minus 1 is equal to 0. Even this is going to be also tough. Okay, let's check it. 2 minus alpha and minus 2 alpha plus alpha square is equal to 1. And this is going to be alpha square minus 3 alpha. No, here is going to be minus 1 is equal to 0. And okay, let's say this is going to be minus 1 is equal to 0. Sorry, 1 plus 1 is equal to 0. Oh god. And let me make it here some entries, easier one entries. Let's say this is 4. No, yes, 4. If I will keep 4 here, then this is going to be minus 4, or let's say minus 4 here. Then this is going to be plus 4. Oh god, let's keep it here 1 itself, minus 1. So here is minus 1. Then this is going to be minus 1. No, it will be plus 1, right? This is going to be, and this is minus of, yeah, this is plus, and here it is plus, and this is 3 now. This is oh god, let's keep it 0. Okay,
I think we can
Let's-
take some
let's
number and proceed. We understand the concept.
yes, let's keep it 0. Yeah, this is 0 here, and this is 0 here, and this is 2 here, and the roots is now going to be 1 and 2. You can check it. So one eigenvalue is 1, and another eigenvalue is 2. And now the processes will take here this one, 1 minus that, whatever this one alpha 1 minus alpha 1, which the first root 0 1 2 minus alpha 1. This is the matrix, and let's writing a general vector and equated to 0. If you see a lecture, if you it will be very much clear that how to find the eigenvector. Easy way, there is a easy to find the eigenvalues, eigenvector. The concept is needed only. Okay, try yourself, watch the lecture, and then we'll discuss more on eigenvalues and eigenvector. But yeah, let's discuss the concept first. So this is the eigenvalue meaning, and meaning is main thing is that here whatever in starting I was discussing this one, how this v's came and why this is the main. Okay, try yourself finding the eigenvalues, eigenvector. I think what is the next one then after getting the eigenvalues, eigenvectors is that I think then geometric multiplication, yeah, diagonalization is there. Okay, and the power of matrix. Okay, so I think algebraic multiplicity and the geometric multiplicity. This is the main thing. So is this clear to find the eigenvalues, eigenvector? This is the process only. This is just a process. Is this clear?
Yeah,
Yes,
yeah.
sir.
But can you just tell us more about this eigenvalue and vector? How it become important in further in advanced courses? I mean, and in
In
the
advanced courses is main on, why this eigenvalue is eigenvector is important when you will do the matrix multiplication. The main of the eigenvalue as eigenvector is the power matrix. Main thing is that whenever we are actually, when you have more data and you want to do multiply more times the same matrix, a square, a cube, or a to the power 100. So
yeah.
how we'll get this? So this will help to get this 100 power matrix, that first find the eigenvalue, eigenvector, change that in the diagonal form, the diagonalization.
Okay.
And then easier to, this will be make easier directly applying on the diagonals only. Find the power of the diagonals only, 2 power 100, 3 power 100, and then just
Okay.
multiply 2, and it will be easier to find. This will be make easier to find the 100 power matrix. This is the only main important, just as of now I know, only I
Okay.
know.
Okay. Understand. Yeah, it makes sense. But
So
do we encounter this kind of matrix in application field? I mean, in somewhere where you're applying it.
yeah, it will be.
Okay.
At least in data science and more, no, I am as a, I think electronic system is there, so there is, I think there is a electronic system uh, courses, I think all of you done, or in the next course in this term is there.
We have done few electronic courses. I mean, 2, 3. We are in now diploma actually. So we have done the foundation level electronic. Yeah.
So actually there is one course, if you remember, if you there is one course in data science, just relating the word, actually uh, in data science there is maths 2 also there, but it here is in more detail. But maths 2 in data science, it is not that much. And what is there, there is a machine learning course, machine learning foundation is there, MLF, which is actually connecting the data science and with the matrix. So here it
Okay.
also, there is one course, and I think sir was saying, Andrew sir is saying that there is one course which connect here, matrix definition, matrix, these all with the electronic systems or electron, whatever. Sorry, in the electricity, what is the thing is the electronic system. So I think there is one course is there. There you will see more important application or more importance of this kind of thing in electronic system.
So it is going to be taught to us also.
I'm not sure. Uh, I don't know where is that. I'm just listen this. I'm not sure who will taught or what is the course name exactly.
Yeah, yeah.
But you will see the application when these application will see ahead. That's all I will say.
Okay. Understand.
And I actually when in this math 2 itself there is a Fourier transformation.
Yeah,
Even in
that.
maths too, these application, this kind of thing you will see in the Fourier transformation itself.
Yeah, yeah.
Eigenvalues, eigenvector matrices, you will see in the Fourier transformation itself. I think after week 8. Yes, I think after week 8 or 6, something is there.
Okay, and in the future we are going to have math 3 also in this electronics course.
Math free.
Yeah.
Sorry, means math will not be there. Is that?
No, no, I'm saying there could be a third math. I mean, this is two math two, correct?
Yes, yeah, there there are lots of maths. Yes.
Yeah. So because I am seeing a lot of like integration and a lot of boundary integration, volume calculation. Those things I think we not covered so far. So
I think those things will cover maybe in that course I'm saying, maybe in that I'm not sure.
okay.
When the foundation will build for when the foundation will be built it for the electronic system, then
No,
in
but
that.
we completed foundation. We are now in diploma actually.
Yeah, I know it, I just know, but I mean to say there is some course is there, I'm not sure, but let's see that. I don't know how the structure is there.
Okay. Okay.
Okay, so that's all. If any doubt is there, we'll discuss. We can discuss here now. Otherwise, in the next session, we'll discuss more. And nothing is remained. So, what is diagonalization? Is that just find the eigenvalues and eigenvectors and write in the in column wise. So, whatever here you are getting, no, the diagonalization is no that whatever you find the eigenvectors, two eigenvector will get v1 v2. We'll write v1 here, v2 here in that matrix column wise, and this is your inverse of the same v1 v2 and inverse. And in this inner part is your eigenvalues. Here your eigenvalues will come, alpha 1 and alpha 2, and this 100 power is nothing but alpha 100 power, alpha 200 power, and these are your eigenvectors. And this is called the diagonalization. We'll actually try to convert the matrix in the diagonalized form. It's called a spectrum also in different word, and this is the meaning. This is another word, is spectrum theorem is called also. But this is the use of eigenvalues and eigenvector. Here this is nothing but your eigenvalues, and this is called, if you are able to, your matrix is able, we are able to write our matrix in this fashion, then we'll say this matrix is diagonalizable. If not, then our matrix is not diagonalizable. So there is one concept is that all matrices are not concept. There is one word is that, or sentence is that all matrices may not be diagonalized also. So some matrices can be diagonalized, some matrices may not be also. Okay, so all matrices are not diagonalizable. So we have to keep in mind this. Okay. Okay.
Yeah. Yeah.
Yes, sir.
Okay. That's all. Any doubt?
Yes,
No.
sir. I have a doubt in activity 2.9.
2.9. 2.9. Okay.
Yes, sir.
Then I have to open just a second. Let me check where is that to stop presenting, and then I have to find where is 2.9. So which activity?
Yes, sir. Question 2.
Question number 2, this one.
Yes, sir.
This is a basis of R2. Consider a linear transformation T and let MT itna be the matrix representation of T with respect to B. What is the matrix representation of T with respect to canonical basis? So this is another basis is given, and I have to find the canonical basis form. How will get this is the problem. So did you try to solve this? This is a good question. It's purposely given to understand the matrix representation. So what is that? How will get this? Actually, it is asking that find the matrix representation. Means we have to find the image of 1 0 and image of 0 1. And let's say these are the entries. Let's say this is, and this is we got, and find so matrix asking that, suppose this is your v1, this is v2, so v1 v2. This is asking, this is the problem. Able to understand or not?
Yes, sir.
So this is the question. When we want to find the matrix representation of T with respect to canonical. Canonical is this one, or 1 0 and 0 1. Okay, what happened? Just a second, it is not working. So, okay, what happened with this? So here is 0 1. This is we want, but we have the this one. So this tells you what? This is the information we have. So could you tell me what is the image of 1 2? Can you tell me what is the image of 1 2?
So this will be 1 into your basis is
Correct.
yeah, 1 into the first basis, and then the second 3 into the second basis. Yeah.
Correct. This is the one. This is we have.
Then similarly for minus
minus 1 and 1 is
2,
1 2.
Yeah.
And 0 time 1 minus 1 1. This is we have. And I want to just find the image of 1 0. This is I want one. This one and P of 0 1. So how we'll get this now? So for this, we have to find the, so here is many thing is there. So change of basis, many thing is there. So this problem is a good one. So we have to, so to find the image of 1 0, what? We have to first find the 1 0 on the basis of 1 2 and on this basis, right? We have to express this, then we are able to do this, correct? If you are able to do, then it is going to be fine. What is going to be if you want to do this, or let's say A, better to write A and B, correct? If we do this, if you are able to express this one on this basis, then now we will try to find the image of this. This is just applying our T of 1 2 plus P of T of minus 1 and 1. which is we can solve here, which is from here directly we can get, which is 1 comma 2 plus minus 3 comma 3, which is minus 2, and this is 5, and this one is what, uh, 2 comma 4 plus 0, which is 0 is there, so that means this one. So if we do this, if we are able to find A and B, then what is that? A time, what is the image of 1 2? Image of 1 2 is this one, plus image of this one is 2 4. So B time minus 2 4. So here is what? So minus 2A 5A plus minus 2B 4B. So once we found this AB, and you know that how to find, correct? Just solving the system of linear equation. Am I audible?
Yes, sir. Yes, sir.
So we know this, no? To find this. Once we find AB, then we are able to get this one, this image. So once we will get the value of A, B, we'll directly, whatever we will get here, we just need to write in that. Similarly, we have to find the 0 1. We have to express 0 1 in the form of A prime 1 2 plus B prime minus 1 and 1. Once we found this, just apply T both side. So A prime T of 1 2 plus B prime minus 1 and 1. Sorry, T of B prime T of minus 1 and 1. And we have already these images. We can substitute and get that. So we have to just find A prime and B prime here for this one, and here A and B for to get this one. This is the canonical basis. That's all. Nothing more. So 2 times we have to solve the system of linear equation. So how much use, see that how much use we are, how many times we are using the system of linear equation. So got the process how to find this?
Yes, sir.
Okay, that's all. I'm just skipping the calculation part now. Okay,
Yes, sir.
any other doubt?
Yes, sir. I have a doubt in practice assignment 1 in some questions.
Practice assignment 1.
Yes.
Could you present your screen? Then otherwise I have to
Yes, sir. I am
yes.
present.
Let me stop. Which question number?
So question number 5.
5. Okay. So is this vector space, or what are the things here? We satisfying the addition property? Okay, for example, I'm saying just take yourself, you do just take minus 1 and x value, just take x value is 1. Okay, so one vector you will get from one vector, not one element of this V, you will get minus 1 and 1, and take the another element, let's say x is equal to 2, then another vector will be what, minus 1 and
Minus 2.
so you have two, minus 1 and 1, and another one is minus 1 and 2. Now add them as you used to, as able to add, you used to add in R2. Could you add these two? What you will get? Minus 2,
2 and 3.
minus 2 and 3. So minus 2
Yes,
and
sir.
3 is element of V. Minus 2 and 3 element of V or not?
I think not,
Why not?
because sir, v is minus 1 comma x.
Yes, because of this reason is because the first coordinate of that, each vector is -1. But we got, after adding them, we got the first coordinate is -2. How it could be?
Yes, sir.
So that's why V is not satisfying the addition property. V is not satisfying the addition property, because if satisfied, then surely it will be of the same, but it is not. Once we added two different vector element, here is not, will call after satisfying the vector space, will call vector, otherwise element will call it as element only. So when we are adding two element, it is not in the V, it is different from V. Similarly, V does not satisfying scalar multiplication. Same way can we check? If we take a scalar, let's say 5, and multiplying with a vector, let's say same 1 and -1, an element of V, not vector, an element of V, -1 and 1. To multiply as you used to do in R2, what you will get?
Minus 5 comma 5.
-5 comma 5. Is that element of V? Again, the
No.
question. No, because the first is should be -1. So again, V is not satisfying the scalar multiplication property. Oh, so your question is that why it is not satisfying, no? So
Yes,
I'm
sir.
saying
Yes, sir.
what it is not satisfying means, are you getting why it is not?
Yes, sir. I'm getting why it
Yeah,
is not.
then fine, because satisfying mean it should be of that form, -1 comma of that. The first coordinate should be of -1, but it is not here. Correct?
Yes, sir.
So let's try for the R statement. That R statement, V has a zero element with respect to addition. So zero element means what? Means, do you have any idea
No
what
element.
is zero element?
I think, sir, no element means 5.
No. Okay, simply I'm saying, I'm just giving you in a real line. I'm just giving 2. So what is the zero
Yes, sir.
element of 2? Do you have any idea what is the meaning of zero element?
No, sir. I have no
Zero
idea.
element is that element when we add in that, it will give 0. That is the word zero element. Means I'm saying 2 is there, then I will add -2 in 2, then it will give 0, right?
Yes, sir.
If I will add -2 in 2, then it will be 0. So zero element of 2 is what? -2. That's the meaning here, zero element. So same way, if I am taking -1 and again x value is 1, okay,
Yes, sir.
and is there any element in that when I add it in -1 comma 1, then it will become 0 comma 0? Could you check that? And if that is there, then it is going to be in V or not? So let me present this, then it will be more clear. Share now.
Yes, sir.
So suppose this one, I'm just taking a element of that V is our -1 comma x, this fashion. I'm just taking a v1, let's say, or V itself, a vector small v. In place of x, I'm just taking 1, so -1 comma 1. So I just said, no, if we have 2, then if I will add in this 2 -2, then it will become 0. So is there any element of these two, so that when I will add here, then it will become 0 0? In this, is there any element in this? So let's find that. So let's find this one. So if I will find AB, so we can write AB as, we can send this to this side. So this will be 1 of minus 1. Correct? Clear?
Eh,
That
yes,
means
sir.
zero element is what? If I, so it tells you that if I have minus 1 comma 1, if I will add here 1 comma minus 1, then it will be 0 comma 0. Correct? So this is our zero element. This is called zero element. Okay. When I'm adding this one to this one, I'm getting this is 0. This is the meaning of zero element. Understood the meaning? So is
Yes,
this
sir.
element in V? Capital V, this V?
No, sir.
No, right? Because here it should be minus 1, then it will be. Otherwise, not. So this is not the element of that. So again, it is not satisfying the. So zero element is not there in V. Understood?
Yes, sir.
And now what is the next statement? Fourth, fifth, I think RS.
V is V is a vector space.
So if these all are actually not satisfied, then how could we that this B could be a vector space? How it could be? How could it will never be. To become a vector space, these all actually should satisfy, but it is not. But this V is not actually satisfying. So how V could be a vector space? So V is not a vector space. So how many statements are actually true now? You can now give the correct statements in that. I think that first one is correct because not satisfying. Second one is also
Yes,
correct.
sir.
Third one is
Yes, sir.
saying not exist or exist.
There exists some
So
element.
it is actually wrong. It is not exist.
Yes, sir.
So two statements are actually correct only. Okay.
Yes, sir.
Any other doubt?
Yes, sir. In question 7,
Of the same grade
this practice.
practice.
Yes, sir. Yes, sir.
Then we have to present then again because I don't have. Could
Yes,
you
sir.
present it?
Yes, sir.
Actually, I need to the fronted X. Still now I didn't get it. Already asked to operational team, but they didn't provide it till now. Okay, seventh problem. I think there is a small error in this. I think you are the same doubt. Uh,
Yes.
Linearly independent and dependent case, right?
Yes, sir. Yes, sir.
So I think it is dependent only because if you check, sorry, independent. It's saying the second option is correct. No, something is there.
Yes, sir.
What is your doubt here first?
Sir, yeah, this linear independent or linearly dependent.
What
This
are
was
the
the doubt.
vectors you have? So what are the vectors you will get after this context? After reading out this context, what are the vectors?
Uh, 3x plus 2y for A, and
3x. You are, why you are saying 3x?
because sir, in question it is saying A acquired 3 units of material X. That's why I'm taking.
So corresponding vector will be 3 comma 2 only, right? You are saying
Yes, yes,
3x.
yes.
So the vector is going to be 3 comma 2, and the another vector is 1 comma 4 for the B. B requires materials 1 unit of X and sorry, 4 unit of Y. So the B vector, you can say B vector is going to be 1 comma 4, and A vector is 3 comma
3
2.
comma 2.
Now we want to check it is these two are linearly independent or dependent. So how we'll check? You have remember that how we'll check.
Yes, sir.
So A time, alpha time first plus
Yes,
beta
sir.
time B, and then equate to 0. Solve the equation, and if alpha and beta are 0, then independent. If not, then dependent.
Yes, sir.
That's the thing only.
And sir, question 8 also.
Suppose the company has 100 unit of material and material X and 80 unit of material Y available for the okay, okay, the same problem. Okay, okay, with the same context. Okay, if K1 unit of product A and K2 unit of product B can be produced without any wasting uh, any material, then find the value of K1 minus 3K2. If given, okay, just a second. This is of week 1 practice assignment, right?
Yes, sir.
Let me present to me. Okay, I am presenting it. You can stop now. So I think now it is correct. I think independent and dependent is met. Yeah, these two are independent. I think yes. The vectors are 3 comma 2 you will get and 1 comma 4 you will get. And you have to check for alpha time A plus oh god plus beta time this one equal to 0 comma 0, and we have to solve this if here is a if A and B become 0, then they are independent. Otherwise anyone is non any one of them is uh, a non-zero, then it will become dependent. Next is company has 100 unit of 100 units of material X and 80 unit of material Y. So okay, so you have okay 100. Okay, so for production, if K1 unit of product A and K2 unit of product B can be produced without wasting any material, then find the value of okay. So here is A product is made of 3 comma 1, sorry, 3 comma 2, and B product is made using uh, 1 comma 4. Okay, now X, sorry, 100 unit of X material is available and 80 unit of B material. Okay, so here is if K1 unit of product A and K2 unit of product B can be produced. So K1, okay, K1 product, I think just a second. Okay, so to manufacture A, we needed 3x and 2y, correct? And to manufacture B, we needed 1 unit of x and y unit of. sorry, 4 unit of y, correct? Am I audible?
Yes, sir.
Okay. So this is we want. Now we have 100 unit of, totally 100 unit of. So here is, a kind of addition is going to be there. So we have x 100 unit of x material. So to produce A, we needed x unit of, 3 unit of material A and 1 unit of material B. So here is what is happening here. K1, because K number of unit of product A produced, right? So that means K number, and then to produce this one. Okay, this is one single A, right? This tells you in making product A this much x and this much y we needed. So K number of is that this much, K time this much of x and this much of y we needed. Similarly, K2 number of B is needed. That means here this 1 and 4. K2 time that B product B. This is your product B, which needed 1 unit of x and 4 unit of y. And this, if you add, so this is, that means 3K1 plus K2. This is your x material, and 2K1 plus 4K2. This is your y material, and this much material is used to, this is total material is exactly our 100 unit of x material and 80 unit of y material, because this unit is used for making this much, right? Are you getting what I mean to say? This one.
Yes, sir. Yes.
So that means here 3K1 plus K2 is equal to 100, and 2K1 plus 4K2 is equal to 80. And how to solve this equation? That's all.
Yes, sir.
Getting right?
Yes, sir. Get it.
Okay. That's all. Any other doubt?
No, sir.
Yeah, thank you. Thank you for your time.
Yeah. Thanks, Pravanjan.
Yeah.
I hope
Thank you, sir.
it's understandable. The class is now okay.
Yeah.
We'll see in the next, I think, algebraic multiplicity and geometric multiplicity. Okay. Thanks.
Yeah. Thanks.
Thanks, everyone.
Thank you, sir. Thank you, sir.
Yeah. Bye. Good night.
Good night. Good night to all of you.